On the Stuve diagram, the horizontal axis shows the air temperature in degrees Celsius, and the vertical axis shows the pressure level in millibar or altitude in geopotential meter, which is very close to physical height in meter. So geopotential height and physical height is very close in values, so we can ignore the difference. The straight green diagonal line here, it shows the so-called dry or unsaturated adiabatic lapse rate. When an unsaturated air parcel rises every 100 meters, the temperature drops -1 degree Celsius. This is because when the air parcel rises, volume expands and the temperature cools to provide the energy to do the volume expansion, which we call the expansion cooling effect. The blue dash or broken curve is our weight or saturated adiabatic lapse rate. For an saturated air parcel, when it rises every 100 meters, the temperature will drop by 0.6 degrees Celsius. Minus simply means the temperature drop. This is because saturated air parcel already condensed, that will release the latent heat to warm up the air. Temperature is still drop, but only by 0.6 degrees Celsius. The other line is here. This is the dash brown straight line, dash brown line, mixing ratio lines, which shows how many gram water vapor per kilogram dry air can hold or already holds. There are two heavy dark curves. The right one is the environmental lapse rate. This is the observed vertical air temperature profile derived from the radio sounding data. And the left heavy curve is a dew point lapse rate. Okay, we call dew point lapse rate. Dew point is the temperature at which saturation or condensation happen. We look at the radio sounding data. At the ground surface, the pressure is about 980 millibar and temperature is 24 degrees. So this is the ground surface level. Dew point is 20 degrees Celsius. So obviously, on the ground surface, the air is not saturated. We can figure out the mixing ratio and saturation mixing ratio. Saturation mixing ratio is derived from the air temperature 24 degrees here. We look at the nearby mixing ratio. This one is 20 gram per kilogram, so it's very close to 20 gram per kilogram. We can interpret as 18 gram per kilogram. Dew point temperature at the 980 millibar of ground surface, there's a mixing ratio line cross the point, and the next line here is 10 gram. So it's probably halfway between 10 and 20 gram. So we can say 15 gram per kilogram. So obviously the air parcel is not saturated because the saturation mixing ratio is 18 gram. Existing mixing ratio determined by dew point is just 15 gram. So when an unsaturated air parcel rises, which should follow the dry adiabatic lapse rate because it's unsaturated air parcel. So we draw a green line parallel to diagonal solid green line. This is the dry adiabatic lapse rate. As far as they are parallel to each other, they have the same slope or same ratio, which is 1 degree decrease in air temperature per 100 meter, increase in altitude. So when this dry adiabatic lapse rate line intersects the mixing ratio line that starts from dew point upward, this is 15 grams per kilogram mixing ratio line. At this point, the air is saturated because now the air parcel can hold on the ground surface, it can hold 18. But when it rises to this 948 millibar level, it's already only can hold 15. But air parcel on the ground surface already have 15 grams, so saturation occurs. This point or this level we call lift condensation level, LCL. This is the expected cumulus cloud base at about 948 millibar height. Starting from this point, the air is already saturated, so it should follow wet adiabatic lapse rate, which is the blue dash curve. So we draw the blue line, heavy blue line, parallel to blue dash curve. Okay, we follow that until this blue line intersects the environmental lapse rate. At this level, that's about, let's look at the height, it's about 600 millibar, I'm sorry. Okay, 600 millibar. So this point, starting from this point, if the air is continuously lift, then what happens? The air parcel's temperature, always warmer than the air temperature or surrounding air temperature or environmental air at the same altitude. So at the same altitude, you can see the air parcel's temperature is warmer. That means the air parcel has a buoyant force. It can automatically rise without the lifting force. So we call this the level of free convection. That's at 600 millibar. So when the air parcel continue automatically rise, intersect another environmental lapse rate somewhere at this point, that's about close to 250 millibar. Okay, very close to 250 millibar. At this point, the air parcel's temperature equals environmental temperature. We call equilibrium level, or you can expect this is the cloud top, or we call level of neutral buoyancy, because from this point, higher air parcel's temperature is colder than environmental air, or the air surrounding the air parcel we call environmental air. So the air parcel is heavier, tends to sink back. Without the lift force, the air parcel will stay here. So we say this is the cloud top. We look at the environmental lapse rate at 144 millibar level. There is an inversion. So this is actually stratosphere. We look at the label here. It's a top. Top means Topeka, Kansas. 72 stands for U.S. Number. 456 is Topeka's station number. This is the radio sounding data, so we call sounding. And tropopause, the top of the troposphere, or the base of the stratosphere, is 144 millibar height. Okay, and level of lift condensation level pressure is 948.5 millibar, which I here show almost the same number. Okay, the difference is very small. What is the lift index? Lift index, I give a number here. It's 500 millibar. At 500 millibar, the lifted index equal to -10 minus 5 degree. So the lift index is equal -5, which is unstable air. Lift index actually equal air temperature minus air parcels temperature at the 500 millibar level. So we look at 500 millibar, air parcels temperature is here, which is close to -10. Okay, because this one shows 0, and air temperature here is close to -10. Air parcel is somewhere between the half, so it's -5. So -10 minus -5 still equal -5. Okay, so we got a -5 lifted index. Total index can be calculated by an equation. There are other index like a Showalter's index. You can find out this later. If you look at the dry adiabatic lapse rate, here dry adiabatic lapse rate and the wet adiabatic lapse rate almost parallel. That means they have the same slope, 1 degree per 100 meter, because here the air is very dry and cold. The air cannot contain much moisture, so moisture is less than 0.1 gram per kilogram. So even the air moisture contains, the latent heat release is minimum. So dry and wet adiabatic lapse rate is almost equal when air temperature is cold or dry, like here, it's in a high level, dry and cold. Under the normal temperature range, somewhere about between -20 degrees to 40 degrees Celsius, the average wet adiabatic lapse rate is -0.6 degree per 100 meter increase in the altitude. The overall purpose of this diagram is to find out the stability of atmosphere, and we find out from the ground surface up to this level of free convection here. You can see air parcels temperature. This is air parcels temperature. First, dry adiabatic lapse rate. Next, wet adiabatic lapse rate. But at the same elevation, altitude, air parcels temperature is always colder than the environmental air. So air parcel tends to sink. Air parcel cannot rise without a lift force, such as a low pressure system move in, or a front move in, or a mountain block the air, make it rise, or solar heating. So we call this layer stable layer because air parcel tends to sink, and air parcel's temperature always colder than environmental temperature. From the level of free convection all the way to the level of neutral buoyancy, here you can see air parcel's temperature is warmer. So air parcel has a tendency, has a buoyancy to rise without lift force. And from this level upward, what happens? Is air parcel stable or unstable? Of course, the air parcel in this layer is stable. Why? Because air parcel's temperature is colder than environmental temperature at the same height. So air parcel tends to sink. So from LNB higher, we find out air parcel is stable. We talk about the lift index, total index. Those are the index used for forecast or predicting occurrence of the severe thunderstorm, either tornado or thunderstorm. We call severe weather. In this case, minus 5.4, which is unstable, and there's a possibility of occurrence of thunderstorm or tornado. Thank you. Bye.